Hello everyone, welcome all to the problem solving session of thermodynamics course on NPTEL. Today I will introduce the concepts of heat engines, heat pumps and refrigeration systems, and then we will solve some problems with these concepts. So first, heat engines. Heat engines are some machines which operate between two thermal reservoirs. The high temperature reservoir is represented by TH and the low temperature reservoir is represented by TL, and this heat engine gets heat energy from the high temperature reservoir, and this rate heat from the high temperature reservoir is represented by QH, and the heat that is rejected to the low temperature reservoir is represented by QL, and it gives an work output represented by W. So now if we do energy balance using first law of thermodynamics, we will get W as QH minus QL, and when we consider the efficiency is represented by desired output by input. So here the desired output is the work output represented by W, and the input given to this system is the QH, that is heat transferred from the high temperature reservoir. So so efficiency is given by W by QH. Here W can be written as QH minus QL, as we saw just now. So this is QH minus QL divided by QH. So this is 1 minus QL by QH. From second law of thermodynamics, we can say that QH by TH is equal to QL by TL. So getting the ratios between the heat transferred between the low temperature reservoir to the high temperature reservoir, we have the ratio between the ratio of the temperatures of the cold and high temperature reservoir, that is TL by TH. So efficiency is also given by 1 minus TL by TH. So that is about the heat engines. Next we have the heat pump. So heat pump is used to transfer heat from a low temperature reservoir to a high temperature reservoir by supplying a work input. So on the bottom we have TL, low temperature reservoir, and QL is transferred from the low temperature reservoir by the heat pump, and heat is rejected to the high temperature reservoir, and the quantity is given by QH, and work transfer W is given to the heat pump for this heat transfer from low temperature reservoir to the high temperature reservoir. Now W can be represented as QH minus QL by doing the first law of thermodynamics analysis. Then here we say coefficient of performance is given again by desired output by input. So for a heat pump, the desired output is the QH, and input given to the system is the work input W. So now this can be written as QH by QH minus QL, and in terms of temperature it is TH divided by TH minus TL. Similarly, for a refrigeration system operating between two temperature reservoirs TH and TL, for a refrigeration system, the desired output is the heat that is taken away from the low temperature reservoir, represented by QL, and the work transfer is again QH minus QL. Now write in COP, which is desired output by input. Here the desired output is QL, and desired in, or the energy supplied is work transfer represented by W. So this becomes QL by QH minus QL. Write in COP in terms of temperature, we have TL divided by TH minus TL. So again the same relation between the heat transfer and the temperature holds the same for all the systems, heat pump and refrigeration system, as we saw in the heat engines. Now moving on to the problems. We have an air conditioner that removes heat steadily from a house at a rate of 750 kJ per minute while drawing electric power at a rate of 6 kW. Determine the COP of this air conditioner and the rate of heat transfer to the outside air. So now we have a refrigeration system. So we have a high temperature reservoir and a low temperature reservoir, and work is supplied to the refrigeration system, and the heat removed from the air conditioned room is 750 kJ per minute. To convert it to kilowatt, we have 750 by 60. So this is 12.5 kilowatt. So QL, which is rejected from the air conditioned room, which is 12.5 kilowatt, and W is given as 6 kilowatt. Now we need to determine the COP. So COP is the desired output by input. So here desired output is QL and desired input is W. QL, heat that is taken away from the low temperature reservoir is 12.5, and work transferred to the refrigeration unit is 6 kilowatt. So 12.5 by 6, we get 2.08 as COP. Next we need to find the rate of heat transfer to the outside air. So that is QH, which is transferred to the high temperature reservoir. So applying first law of thermodynamics, we have W is equal to QH minus QL. So QH is equal to W plus QL, and W is 6 kilowatt and QL is 12.5 kilowatt. So that means QH is equal to 18.5 kilowatt. To convert this to kilojoule per minute, we can multiply this with 60. So that will be 1110 kilojoule per minute. So kilowatt is kilojoule per second. So for every second we had 18.5 kilojoules. Then for every minute we will have 18.5 into 60 kilojoules. Moving on to the next problem. We have an household refrigerator that has a power input of 450 watts and a COP of 2.5, and that is to cool 5 large watermelons 10 kg each to 8 degrees Celsius. The watermelons are initially at 20 degrees Celsius. Determine how long it will take for the refrigerator to cool them. The watermelon can be treated as water whose specific heat is given by 4.2 kilojoule per kilogram. 4.2 kilojoule per kg degree Celsius. And is your answer realistic or optimistic? Explain. So representing the representing the refrigeration system, we have a power input of 450 watts. So and QH. So COP is 2.5. That means QL by W is 2.5. So QL can be calculated as 2.5 W, which is 2.5 into 450. So this is 1125 watts. Now we know this is the rate at which the heat is transferred from the low temperature reservoir. Now this is to cool some watermelons, 5 large watermelons, 10 kg each. So mass of the total system is 5 into 10, which is 50 kg, and delta T is 20 minus 8, which is 12 degrees Celsius, which has to be cooled down. And how long it will take, and yeah, C is given as 4.2 into 10 power 3 joule per kg degree Celsius. So now we have Q dot is into time is equal to MC delta T. So time is MC delta T divided by Q dot. So this is M is 50 into C is 4.2 into 10 power 3 into delta T is 12 divided by the Q dot, which is 1125. So the answer is 2240 seconds. I hope this problem is clear. Moving on, the next problem, we have a man who returns to his well sealed house on a summer day. He finds the house is at 32 degrees Celsius. He turns the air conditioner, which cools the entire house to 20 degrees Celsius. So T initial is equal to 32 degrees Celsius, T final is 20 degrees Celsius, and time taken is 15 minutes. So this is 15 into 60 seconds. So this is 900 seconds. If the COP of the air conditioning system is 2.5, so COP is given as 2.5. Determine the power drawn by the air conditioner. Assume the entire mass within the house is equivalent to 800 kg. So that is M is 800 kg. And CV and CP of the air is given. So this is a well sealed house, so it is a constant mass system, and the heat to reduce the temperature of the constant volume system, we have Q is equal to MCV delta T. So now we can calculate the heat that has to be transferred for the rate at which the heat has to be transferred. So Q dot is given by MCV delta T by time. So this is M is 800 kg and CV is given to as 0.72 kg per kilojoule per kg, which is 720 joule per kg. So I have 720 here into delta T is 32 minus 20 divided by time taken, which is 900 seconds. So I have Q dot. So Q dot is 7680 watts. Now COP is given, we need to find the power that is drawn by the air conditioner. So COP is Q dot by work input, so which means work input is Q dot by COP, which is 7680 divided by 2.5. So that is 3072 watts. I hope this problem is clear. Moving on, in the next problem we have a heat pump that is used to maintain a house at a constant temperature of 23 degrees Celsius. The house is losing heat to the outside air through the walls and the windows at a rate of 60,000 kilojoule per hour, while the energy generated within the house from people, lights and appliances amounts to 4000 kilojoule per hour. For a COP of 2.5, determine the required power input to the heat pump. So we have an house. So from the house 60,000 kilojoule per hour is lost, and from the appliances some 4000 kilojoule per hour is generated, and for a COP we need to find the required input. So that means the net energy that has to be supplied by the heat pump is, I would write this as Q heat pump, is 60,000 minus 4,000, because 4,000 is generated and 60,000 is lost, so the difference alone can be supplied by the heat pump, which is 56,000 kilojoule per hour, which is 56,000 divided by 3600 joules per second. So this is 15.55 kilowatts. Now COP of the heat pump is COP of the heat pump is heat that is transferred by the heat pump divided by the work input, which is equal to 2.5, which means work, the rate of work is QHP divided by COP. So QHP is 15.55 and COP is 2.5. So that means work transfer rate is 15.55. So this is 6.22 kilowatts. I hope the problem is clear. If you have any questions, you can ask. Okay, moving on to the next problem. We have a Carnot heat engine which operates between a source and a source at 1000 Kelvin and a sink at 300 Kelvin. If the heat engine is supplied with the heat at a rate of 800 kJ per minute, determine the thermal efficiency and the power output of this engine. So we have an heat engine, Carnot heat engine, which has 1000 Kelvin as a high temperature reservoir and 300 Kelvin as low temperature reservoir, QH and Q low. L represents the heat transferred from the high temperature and the low temperature reservoirs, and we have work output. Now the heat supplied is 800 kilojoule per minute. So this is 800 by 60 kilojoule per second. And this is 13.33 kilowatts. Now we can calculate the thermal efficiency. Thermal efficiency is given by 1 minus temperature of low temperature reservoir by temperature of high temperature reservoir, which is 1 minus 300 by 1000, which is 0.7 or 70%. And efficiency is desired output by input. So here the desired output is W and energy supplied is QH, which is 70% now, and that means W is efficiency into QH. Efficiency is 0.7 into QH is 13.33 kilowatt. So W can be calculated, which is 9.33 kilowatt. I hope the problem is clear. In the next problem, there is an innovative way of power generation which involves the utilization of geothermal energy, the energy of hot water that exists naturally underground, as a heat source. If a supply of hot water at 140 degrees Celsius is discovered at a location where the environmental temperature is 20 degrees Celsius, determine the maximum thermal efficiency a geothermal power plant built at that location can have. So we have a high temperature reservoir at 140 degrees Celsius, and we are supposed to run a heat engine to generate power from this high temperature source, and the sink is the atmosphere, which is 20 degrees Celsius. Now converting the temperatures to Kelvin, we have 413 Kelvin for the high temperature reservoir and 293 Kelvin for the low temperature reservoir. So we can calculate the efficiency as 1 minus TL by TH, which is 1 minus 293 by 413. This is 0.29055, or efficiency is 29.1%. Moving on to the next problem. A geothermal power plant uses geothermal water extracted at 160 degrees Celsius at a rate of 440 kilogram per second as the heat source and produces 22 megawatt of net power. If the environmental temperature is 25 degrees Celsius, determine the actual thermal efficiency, the maximum thermal efficiency possible, and the actual rate of heat rejection from this power plant. So drawing the schematic of the power plant, we have high temperature reservoir at 160 degrees Celsius and low temperature reservoir at 25 degrees Celsius. Converting the temperatures to Kelvin scale, we have 433 Kelvin for the high temperature and 298 Kelvin for the low temperature. the heat, the water which is applied has a flow rate of 440 kilogram per second. I write it as m dot, and power produced is 22 megawatt. So now I can calculate q dot h, which is m dot c into T. So here m dot is 440 into C is C of water, which is 4.2 kilojoule per kg Kelvin. So I write it as 4.2 into 10 power 3 joule per kg Kelvin into temperature. We have the high temperature reservoir as 433 Kelvin. So this comes out to be 800.184 into 10 power 6 joules per second, which is 800.2 megawatt. So that means we can calculate the actual thermal efficiency now. Eta act is W dot by Q dot H, which is 22 divided by 800.2. So this is 0.0275, which is 2.75%. Now we can calculate the theoretical or the maximum possible thermal efficiency, eta max, which is given by 1 minus TL by TH. Here TL is 298 and TH is 433. So that means maximum thermal efficiency possible is 0.3118, which is 31.18%. Now the actual rate of heat rejection from the power plant has to be calculated. So that is QL. QL is QH minus W. So actual QH is 800.2 and actual W is 22. So we have 778.2 megawatt, which is rejected. Moving on to the next problem, we have a Carnot refrigerator which operates in a room in which the temperature is 22 degrees Celsius and consumes 2 kilowatt of power when operating. If the food compartment in the refrigerator is to be maintained at 3 degrees Celsius, determine the rate of heat removal from the food compartment. So we have a refrigerator which has a low temperature reservoir of 3 degrees Celsius. So 3 degrees Celsius is 276 Kelvin, and high temperature reservoir is 22 degrees Celsius, which is 295 Kelvin. The energy supplied to the refrigeration system is 2 kilowatt. Now we have to calculate the heat removed from the food compartment. So QL is to be calculated. So we can calculate the COP. COP is given by desired output by input. Desired output here is QL and desired input, the energy input is W, and W is given by QH minus QL. So this can be written using temperatures as TL divided by TH minus TL. So TL is 276 and TH is 295, TL is 276 again. So we have COP of 14.5. So now QL can be written as COP into W, and here COP is 14.5 into W is 2 kilowatt, so this becomes 29 kilowatt. I hope this problem is clear. Moving on, we have an air conditioning system which operates on the reverse Carnot cycle and is required to transfer heat from a house at a rate of 750 kilojoule per minute and to maintain the temperature at 24 degrees Celsius. If the outdoor air temperature is 35 degrees Celsius, determine the power required to operate this air conditioning system. So we have a refrigeration system working based on the reverse Carnot cycle. The high temperature reservoir is the outdoor temperature, which is 35 degrees Celsius. So 35 converting to Kelvin scale, we have 308 Kelvin. So this is 35 degrees Celsius. And similarly, we have a low temperature reservoir maintained at 24 degrees Celsius. So converting to Kelvin scale, we have 297 Kelvin, and there is a work input that is given to the refrigeration system. Here QL is given as 750 kilojoule per minute. So this can be written as 350 by 60 kilojoule per seconds. Which is 12.5 kilowatts. Now we need to calculate the work input. So I will make use of the COP formula. COP is QL by W, which is desired output by work input. So W can be rewritten as QH minus QL. So writing in terms of temperature, we have TL by TH minus TL. So COP is 297 divided by 308 minus 297. So this is 27. Now to calculate W, we have QL divided by COP. QL is given as 12.5 and COP is 27. So we have W as 0.4629 kilowatt. I hope this problem is clear. Moving on, we have a reversible heat engine which operates between two reservoirs at temperature of 600 degrees Celsius and 40 degrees Celsius. So reversible heat engine. So TH, I will convert to Kelvin scale. which will be 873 Kelvin. Heat transfers from the high temperature reservoir to the heat engine, and heat engine rejects the heat to a low temperature reservoir which is at 40 degrees Celsius. So 40 is 313 Kelvin, and this gives an work output. I would write the Q1 as heat transfer from the high temperature reservoir to the heat engine, and Q2 as heat transfer from the rejected by the heat engine to the low temperature reservoir. And this engine drives a reversible refrigerator which operates between reservoirs at temperature 40 degrees Celsius and minus 20 degrees Celsius. So we have a refrigeration system to which I would write this W as W1, and work supply to the heat refrigeration system as W2, and again it has contact with two thermal reservoirs. I would write the heat engine thermal reservoirs as TH1 and TL1. For the refrigeration system, that high temperature reservoir is TH2, which is at 40 degrees Celsius, which is 313 Kelvin, and it has so heat transfers from low temperature reservoir to high temperature reservoir in a refrigeration system. The low temperature reservoir for the refrigeration system is minus 20 degrees Celsius, which is 253 Kelvin. The heat transfer to the heat engine is 2000 joules, so that is Q1 is 2000 kilojoules, and the net work output of the combined engine refrigerator plant is 360 kilojoules. So that means W1 minus W2 is 360 kilojoules. In the first section of the problem, we need to evaluate the heat transfer to the refrigerant and the net heat transfer to the reservoir at 40 degrees Celsius. So I would write this as Q3 and Q4. The heat transfer to the refrigerant and the net heat transfer to the reservoir is to be found. First I would calculate the efficiencies. Efficiency of the heat engine is 1 minus TL1 by TH1, which is 1 minus 313 by 873. So this is 0.6415, so which is 64.15%. And calculating the COP of the refrigeration system, we have this is Q4 by Q3 minus Q4, which is 253 Kelvin in terms of temperature. Write the formula first. TL2 divided by TH2 minus TL2. So this is 253 divided by 313 minus 253. So this is 4.217. This is COP of the refrigeration system. Now to calculate the work W1 given by the first heat engine, we have Q1 into efficiency, which is Q1 is 2000 kilojoules and efficiency is 0.6415. So that means W1 is 1283 kilojoules. So and it was said that the net output of the work output of the combined plant is 360 kilojoules. So that means W1 minus W2 is 360, which implies W2 is W1 minus 360 kilojoules, which is 1283 minus 360. So that is 923 kilojoules. So now we have the COP of the refrigeration system and the work input to the refrigeration system. Using this we can calculate the values of Q3 and Q4. So COP of the refrigeration system is Q4 divided by W2. Here Q4, okay, so that means Q4 is COP of the refrigeration system into W2, which is 4.217 into 923, which is 3892.3 kilojoules. So now Q3 can be calculated. Q3 is Q4 plus W2 using the energy balance, and Q4 is 3892.3 plus work output is 923, which means Q3 is 4815.3 kilojoules. Now we were asked to evaluate the heat transfer to the refrigerant, so that is Q4. We have calculated Q4 here, and the next part of the problem is to calculate the net heat transfer to the reservoir at 40 degrees Celsius. So the heat engine also had a thermal reservoir at 40 degrees Celsius, and heat supplied to the heat rejected to the reservoir 40 degrees Celsius reservoir by the heat engine is Q2, and that is calculated earlier. Okay, so that is not calculated, you can calculate that. And we have a refrigeration system, again that also transfers heat to the thermal reservoir at 40 degrees Celsius. So, and that value is given by Q3. So net heat transfer to 40 degrees Celsius reservoir is equal to Q2 plus Q3. I need to calculate Q2. This is given by Q1 minus W1, and Q1 is 2000 kilojoules minus W1 is 1283. So I have Q2 as 717 kilojoules. So I can calculate Q2 plus Q3 as 717 plus 4815.3. So that is 5532.3 kilojoules. This is a net heat transfer to the 40 degrees Celsius reservoir. Now we have to reconsider the problem, given that the efficiency of the heat engine and the COP of the refrigerator are each 40% of their maximum possible values. So in the part A of the problem, we had their maximum possible values for the efficiency and COP, and that was 64% for the efficiency of heat engine and 4.2 for the COP. So now for the second part we have to take 40% of their maximum value. So for the B part, efficiency of the heat engine, I write it as theta efficiency eta dash, which is 40% of eta He. So 0.4 into 0.6415. So eta dash is 0.4 into 0.6415, which is 0.2566 or 25.66%. Similarly, the new COP dash is 0.4 times of the maximum possible COP, which is 0.4 into 4.217. So the new COP is 0.4 into 4.217, which is 1.6868. Now we have to recalculate all the values. So now W1 is Q1 into eta dash. Q1 was 2000 joules and efficiency is 0.2566. So this is 513.2 kilojoules. Now we can calculate Q2 first. Q2 is Q1 minus W1, which is 2000 minus 513.2, which is 1486.8 kilojoules, and W2 is given by W1 minus 360, which is 513.2 minus 360, that is 153.2 kilojoules. Now we can calculate the Q4. Q4 is COPR dash into W2, which is the new COP is 1.6868 into W2 is 153.2. So that is 258.42 kilojoules. Now we have Q3, which is Q4 plus W2, and that is 258.4 plus W2, which is 153.2. This is 411.6 kilojoules. So again the heat supplied to the refrigerant is represented by Q4, and that is 258.42 kilojoules, and total heat transferred to that reservoir at 40 degrees Celsius is Q2 plus Q3. Q2 plus Q3, and we had Q2 as 1486.8 plus Q3 is 411.6. So this is 1898.4 kilojoules. I hope the problem is clear. In the next problem, we have a heat pump working on a Carnot cycle that takes in heat from a reservoir at 5 degrees Celsius and delivers heat to a reservoir at 60 degrees Celsius. So representing that, we have a heat pump which takes heat from a lower temperature reservoir at 5 degrees Celsius. So 5 is 278 Kelvin, and supplies heat to a high temperature reservoir at 60 degrees Celsius, and that is given by, so that is 333 Kelvin. And this heat pump is driven by a heat engine that takes in heat from a reservoir at 840 degrees Celsius and rejects heat to a reservoir at 60 degrees Celsius. So we have a heat engine, and that transfers the heat to the heat pump, and the high temperature reservoir is at 840 degrees Celsius. I represent this by TH2, and for the heat pump I have TH1 and TL1 as the reservoir temperatures. So the low temperature reservoir for the heat engine is TL2, which is at 60 degrees Celsius, and that is 333 Kelvin. So this the TH2 is 1113 Kelvin. Now the reversible heat engine also drives a machine that absorbs 30 kilowatt. So that means the entire energy from here doesn't go here. So I say W1 is transferred to the heat pump, and W2 is generated by heat engine, and W2 is W1 plus 30 kilowatts. If the heat pump extracts 17 kilojoules per second from the 5 degrees Celsius reservoir, so that means this value is 17 kilowatt. Determine the rate of heat supply from the 840 degrees Celsius source and the rate of heat rejection to the 60 degrees Celsius sink. Now I represent these heat transfers as Q1, Q2, Q3 and Q4. First I would calculate the COP values, COP and the efficiency values. COP of the heat pump is Q1 by W1, which is Q1 by Q1 minus Q2. In terms of temperature, we have T1 by T1 minus T2. So this is 333 divided by 333 minus 278. So this is 6.05 is the COP of the heat pump. Now to calculate the efficiency of the heat engine, we have 1 minus TL by TH. So here it is TL2 by TH2, and that is 1 minus 333 divided by 1130. So this efficiency is 70%. So now we can calculate the heat, that is determine the rate of heat supply from the 840 degrees Celsius source. So first I can calculate W1 using the COP value. W1 is Q2 divided by COP of the heat pump. Since it is an heat pump, we had Q1 minus Q2. So COP says that Q1 is equal to COP heat pump into W1, and we know from the energy balance equation Q1 is equal to W1 plus Q2. So substituting the Q1 value from the COP expression, we have COP HP into W1 is equal to W1 plus Q2. So which means COP heat pump minus 1 into W1 is Q2. So W1 is Q2 by COP heat pump minus 1. So this is Q2 is 17 kilowatt and COP is 6.05 minus 1. We have 3.366 kilowatt as W1. Now I can calculate W2. So W2 is W1 plus 30, which will be 33.366 kilowatt. I had efficiency as 70%, so that means efficiency is W2 by the heat transfer from the high temperature reservoir, which is Q3. So I can calculate Q3 as W2 by heat efficiency, which is 33.366 divided by 0.7. So Q3 is 47.66 kilojoules, sorry, kilowatt. So this is the first part of the problem, and the second part is to calculate the rate of heat rejection to the 60 degree Celsius sink. So that is heat transfer to 60 degree Celsius sink is from the heat pump in terms of Q1, and from the heat engine it is Q4. So this is Q1 plus Q4. Q1 is just calculated as 3.366 and Q4 is yet to be calculated. So Q4 is Q3 minus W2. So Q3 is 47.66 minus W2 is 33.366. So this is 1.428 kilowatt is Q4, and Q1 is already calculated. So Q1 is, it's not calculated. No. Q1 is COP of the heat pump into W1, which is 6.05 into W1 is calculated as 3.366. So this is 20.36 kilowatt. So Q1 plus Q4 is equal to 1.428. Sorry, this is not 1.428. This is 14.29 kilowatt. So Q1 is 20.36 plus 14.29. We have 34.65 kilowatt. So So this is the total heat that is transferred to the 60 degrees Celsius sink. Yeah, thank you for attending the session. If you have any queries, you can ask in the discussion forum, and I will be able to answer your questions. Thank you. We will see you in the next session.